Okay, people have had some time to get here. Um, so, a reminder, worksheets 15 through 22 are due on the 30th. That's Thursday. Homework number 3 is also due on the 30th. That's Thursday. Test number 3 will be in class here in person on Thursday. It's just like the previous test, 60 questions, Scantron. You get a sheet of notes, but you have to be here to take the test. If you're not able to make it, please let me know in advance. And please sign in on the sign-in sheet if you are here. So we were talking about the deaths of stars. So at the end of large stars' life, we get fusion continues until iron builds up in the core. No energy is gained from fusing iron. It takes energy to fuse iron. And as the mass increases, electrons get pushed into the nucleus, forming neutrons. And degenerate neutron pressure can now keep the core from collapsing, even if only for a moment. Oh, it helps if you turn this off. It helps if you plug it in. Jeez. Sorry about that. Apparently bits of my brain are not fully activated this morning. So the core will quickly collapse from something the size of Earth to something about 20 kilometers in size. And the generous suppression of the neutrons will then support the core, and the core will become neutrons. So the rebound of material as it strikes the neutron core creates a shock wave that moves throughout the star. And this disrupts the outer layers and it expels them out into space. And this is called a type 2 supernova explosion. And after a supernova explosion, it leaves behind a remnant in the outer layers of the star. And the core gets compressed and can form into one of two things, either a neutron star or a black hole. It will always form a neutron star like temporarily, at least for a moment, and then that neutron star will collapse. But this process actually is why the supernova goes off. So the remnants behind from large stars can either be neutron stars or black holes. So here is a short video about those remnants.
Objects even more extreme than white dwarfs form when massive stars end their lives. Recall that a massive star supernova occurs when a final stage of fusion gives the star an iron core, and that iron cannot release energy. The core therefore implodes catastrophically, and because its mass exceeds the white dwarf limit, electrons combine with protons to make neutrons. The release of gravitational potential energy drives the outer layers outward as a supernova, and the core collapse halts when the neutrons are packed as closely as the laws of quantum mechanics allow. Neutrons can be packed much closer together than electrons, so this neutron degeneracy pressure leaves a neutron star only about 10 kilometers in radius. The first evidence for neutron stars came with the detection of very regular pulses of radio waves. Astronomers deduced that the pulses were coming from spinning neutron stars, also called pulsars, in which the spin axis is not aligned with the neutron star's strong magnetic field. The spinning neutron star therefore acts much like a lighthouse, in which beams of radiation sweep through space, and we see a pulse each time a beam sweeps past us. Astronomers are confident in this model because pulsars are indeed found at the centers of massive star supernova remnants, such as the Crab Nebula. This video shows the pulsar at its center. Just as there is a limit to the mass of a white dwarf, there is also a limit to the mass of a neutron star. For a collapsing stellar core with more than about 3 solar masses, neutron degeneracy pressure is not strong enough to overcome the crush of gravity, and the collapse continues without limit.
And that video of the pulsing neutron star, normally often about stuff in space, we'll say, okay, we sped it up so you can see it more easily. That actually had to be slowed down so you can see it more easily. The star in the Crab Nebula pulses like 20 or 30 times a second. So, what is a neutron star? Well, a neutron star is basically what happens when you squeeze a big ball of matter until all the electrons merge with the protons, and you essentially get just a giant nucleus. So a neutron star is the ball of neutrons left behind after a massive star supernova, and it's supported by, instead of the degeneracy pressure of electrons, which is what supports white dwarfs, it's supported by the degeneracy pressure of neutrons. So neutrons, like electrons, are fermions, so you can't have two of them doing the same thing in the same place. So you can get a neutron star. But because neutrons are neutral and other properties of the neutrons, they're denser than electrons, basically, you can make a neutron star much smaller. Electron degeneracy pressure goes away because electrons combine with protons, making neutrons and neutrinos. The neutrons collapse to the center, forming a neutron star. The neutrinos travel outwards. Now, neutron stars are small. They're about the same size as a small city, but they're between 1.4 and 3 solar masses mass. So they're the densest thing that is a thing in the universe. You know, the densest stuff in the universe is neutron star matter, or neutronium, if you want the fancy name for it. And you may have seen that in video games. It shows up, neutronium, because it sounds cool and makes for a good end game material. Neutron stars. So they have about 1 to 3 solar masses. They're so dense that they're actually quite small. Again, 10 to 20, 10 kilometers in diameter. 1 solar mass neutron star, about 10 kilometers in diameter, compared to Manhattan. They're the size of like downtown. Well, a bit bigger than downtown, but they're not very big. Some other properties of neutron stars. Because they started big and got so small, they end up spinning very fast because of conservation of angular momentum. So generally, neutron stars spin many times a second. Their periods are a fraction of a second. So the one in the Crab Nebula, I believe, spins about 30 times a second. There are faster ones and slower ones. Also, because of the collapse, these end up with the strongest magnetic fields of any objects in the universe. Because neutrons have magnetic fields, and the magnetic field of all those neutrons compressed so densely is significant. So neutron stars are spinning very fast and they have a magnetic field, but that magnetic field is not necessarily aligned with their rotation. And that ends up causing them to basically shoot out beams of energy along the poles of their magnetic fields, and like a lighthouse, sweep across space and light up Earth, which we see as pulsars. So the discovery that neutron stars actually existed was in 1967 by Jocelyn Bell, who was a research student, and found a very unusual radio signal. Because it was perfect, it seemed like it was perfectly regular, perfectly evenly spaced. So here's that signal. So these extremely regular emission pulses with a period of 1.33728 seconds. So the question was like, what kind of object could create these short pulses? And in fact, there was a note on one of these records of LGM from Little Green Men. There was the thought it might be artificial. So there was a moment where people were like, maybe this is aliens. Because it's so regular and repeated. But more study made them realize that no, this is actually a neutron star. So once they started to figure out that this is something spinning very fast, and they needed to figure out what it could be. So no ordinary star could spin that fast without tearing itself apart. So one possibility for something happening regularly is a spinning object that's emitting energy in a direction. And similar objects to this were discovered, which really kind of threw out the artificial. And one of them, for example, the Crab pulsar is spinning 30 times a second. But neutron stars were a theorized object. People have theorized that such a thing as a neutron star could exist. I started working out what would happen if the core of a dead star collapsed. And so this could be a neutron star, the compact core of a dead star that's about the size of a city. So the first pulsar was discovered in 1967. It emitted extraordinarily regular pulses, nothing like it had been seen before. And after some initial confusion, it was realized it was a neutron star spinning very rapidly. This is actually on the slower end. The first pulse was actually a bit on the slower end for neutron stars, as it pulses like more than once a second. The pulse is a bit on the slower side, not the slowest. So, for example, the pulsar at the center of the Crab Nebula pulses 30 times per second. Amusingly, from our point of view, there's another pulsar right behind it, right next to it. So you can see the two pulsing at different rates. So a pulsar is a neutron star that beams radiation along a magnetic axis that is aligned with the rotation axis. So what happens is that as material falls into the neutron star, it generates, as the star spins, it generates radiation, and you get beams shooting out along the magnetic axes. And that energy is what we see as a pulsar. So the radiation beams sweep through space like lighthouse beams as the neutron star rotates. So not all pulsars are visible. Not all neutron stars that are generating these beams are visible as pulsars from Earth, because the beam has to be following a path that hits Earth. If it misses us, then we wouldn't see it. We have identified neutron stars just floating around as well. Though it's much harder, it's much easier to find pulsars. So the pulsar lighthouse model is that the pulsar behaves like a lighthouse. As the star collapses, its magnetic field intensifies, and you get beams of particles emitted along the magnetic axis. Because otherwise they'd be trapped in the magnetic field, but along the magnetic axis they can escape. And this generates streams of radiation. So when do we see a pulsar? Only when the beam points towards Earth. So many pulsars remain invisible to us because their beams never point in our direction. So if the beams of a pulsar never point in our direction, we don't see it as a pulsar. So if you think about why this neutron star flashes on and off, it's because there's this beam that passes by and hits us repeatedly. Like if you were looking at a lighthouse, a lighthouse would appear to flash on and off. So strong jets of matter are emitted at the magnetic poles, where they can escape. And if the rotation axis is not same as the magnetic axis, these would sweep out circular paths. And if the Earth lies in one of these paths, we'll see the star blinking on and off. So what is the evidence that pulsars are rapidly spinning neutron stars? Well, the masses measured for pulsars are in the correct range, because we can measure the masses because many of them are in binaries or things like that. Pulsar beams energize the nebula they're in to keep it glowing. And we can actually calculate that where this energy comes from that energizes the nebula. So what is the energy that energizes the nebula? Well, the rotation of the neutron star will gradually slow. And observations show that the energy lost from the pulsar, how much, because we can work out how much energy the pulsar is putting out by how much the nebula flows, because it's getting dumped into the nebula, is equal to and then we can work out how much energy the pulsar is losing from its spin, like how much it's slowing down, and we find that the energy lost from the pulsar is equal to the energy being emitted from the nebula. So that's another good sign that our model of it being a neutron star spinning very quickly is correct. So, why pulsars have to be neutron stars? So the circumference rate of a neutron star is about 60 kilometers. 2 pi times the radius. The spin rate of a fast pulsar is 1,000 cycles per second. So that puts the surface rotation velocity of this object at something like 60,000 kilometers per second, or 20% of the speed of light, or around the escape velocity from a neutron star. Anything bigger would be spinning even faster, and would tear itself apart. So anything else would be torn to pieces because its surface would be moving even faster. So basically, tells us the only thing that could spin that fast is a neutron star. And pulsars change over time. They live about 10 million years. They finally slow down enough that the pulses can't be seen. So they're just pulsing on and off for a few million years. And as the energy decreases, the pulses are no longer seen at short wavelengths, only as radio pulses. So faster spinning, younger, faster new pulsars emit shorter wavelengths. Now, neutron stars are difficult to detect. They're small, and so subsequently they are dim. If the pulses aren't pointing towards Earth, we can't see them. Or if they're spinning too slow to generate pulses, they're both, in both of these cases, it's very hard to see. Now, a lone neutron star was detected in 1992. It's about 400 light years away. It's about 14 kilometers in size, and it is incredibly hot. Its surface temperature is half a million degrees Kelvin. So pulsars will radiate their energy away quite rapidly. The radiation weakens and stops in a few tens of millions of years, making the neutron star virtually undetectable. And pulsars are also not going to be visible on Earth if the jets don't sweep past our way. So some examples. There's a pulsar at the center of the Crab Nebula. Here's the pulsar off and on. So it switches between on and off as the beams point towards us. The Crab pulsar also pulses in the gamma ray spectrum, as does the nearby Jaminga pulsar. So here you can see both the Crab pulsar pulsing and the nearby Jaminga pulsar. So the Jaminga pulsar is on top, the Crab pulsar is on the bottom here. So they pulse at different rates, but you can see both pulsars here in gamma ray. And an isolated neutron star was observed by the Hubble telescope. It's moving rapidly. It has a surface temperature of around 700,000 Kelvin. Different sources are a little different, and it's about 1 million years old. So here's some observations of it over time. So neutron stars were first discovered as pulsars, and they're rapid bursts of radio emissions. The lighthouse model explains the pulses and why we do not see all neutron stars as pulsars. They slowly lose their energy as they age, and eventually the pulses stop and the neutron star remains. Neutron stars are very weird objects. just in general, because giant ball of neutrons is strange. So compact stars, like neutron stars or white dwarfs, could be in binary systems. So we've looked at individual compact stars, like neutron stars or white dwarfs. What happens if one of these stars is in a binary system? Well, there's a number of things that can happen. There are things like novae, supernovae, X-ray bursts, and gamma ray bursts. The first two involve white dwarfs. The second two involve neutron stars. So with a white dwarf in a binary system, material can accrete from the white dwarf's partner onto the white dwarf, leading to a sudden increase, and as it builds up, there can be a sudden onset of hydrogen fusion, leading to a sudden brightening of the star. So if the two stars are close enough, material from the not a still living star can accrete on the white dwarf. Material can transfer from the star to the white dwarf. This creates an accretion disk around the white dwarf, and hydrogen will build up on the surface. And if this becomes hot enough, fusion will start on the surface of the white dwarf, and the star will become hundreds or thousands of times brighter. And this can happen multiple times in the same system. As hydrogen builds up, fusion occurs, and the process repeats. Now, there is a limit to this, because as this buildup of material occurs on a white dwarf, if this transfer of material pushes the white dwarf over the 1.4 solar mass limit, then instead of just fusion at the surface and sudden brightening, the white dwarf will start to collapse because it can no longer support itself against gravity. And fusion of carbon will begin in the entire star at the same time, and the whole star will basically go off like a bomb and disintegrate. And that'll tear the star apart, and there will be nothing remaining. So the two types of supernovae are type 2 supernovae, which are the deaths of massive stars. It's the explosion of a massive star at the end of its life. You get a neutron star or a black hole left behind, and you'll see strong hydrogen lines in the spectrum. And type 1, which is when a white dwarf star exceeds the 1.4 solar mass limit and explodes. Absolutely nothing is left behind. You do not see hydrogen lines in the spectrum. And these are important for determining distances to distant galaxies. These are a standard candle, because each of these is the same type of object exploding. They should all have the same luminosity. So if you see it far away, you know how bright it is, because you know what it is and that it's exploding. So you can figure out how far away it is from how bright you see it. Specifically, they use type 1A supernova. Now, if you have a neutron star in a close binary system, similar things can occur. Material can accrete on the neutron star until it violently explodes with fusion or whatever, and other things like that. So matter forming towards a neutron, falling towards a neutron star will form an accretion disk, just like matter falling towards a white dwarf. It will heat up. And one of the things it can do is it can add angular momentum to a neutron star. It can make a neutron star spin faster, increasing its spin. And when you get episodes of the fusion on the surface of a neutron star, you get what are called X-ray bursts. You get sudden, violent releases of X-rays at the surface of the neutron star. So this is like a nova, but for a neutron star. It's an X-ray burst. But one of the things that the same falling matter spinning up the neutron star gives us helps explain one of the things we've seen, which is the very fast pulsars. Because we've observed pulsars, which are called millisecond pulsars, which are spinning too fast to just have gotten their spin from the collapse of the original star. So something must have made them spin faster. And that is material falling onto them, causing them to speed up. So matter accreting onto a neutron star, it eventually becomes hot enough for helium to fuse. So not just hydrogen fusing, but helium fusing. And the sudden onset of fusion produces a burst of X-rays. So you get transfer of mass from a companion like a white dwarf, material will build up on the surface. And because of the strong gravity and extremely high temperatures, you can get bursts of X-rays from the surface. And we have detected these X-ray bursts. And the right sort of positioning of material falling onto the neutron star can speed it up, leading to what are known as millisecond pulsars. These pulsars that are spinning faster than they could have ended up spinning from just the death of a massive star. The bursts of X-rays have been observed from the center of our galaxy. A typical one appears on the right. So this is before, and this is during the burst. And this is in the X-ray spectrum. So before it's glowing in X-rays, and during it's much brighter. And these X-ray bursts are thought to originate in neutron stars that have binary partners. And the process is very similar to a nova, but much more energy is emitted due to the extremely strong gravitational field of the neutron star, concentrating everything closer together, making the whole thing more violent. Now, most pulsars have periods between about 0.03 and 0.3 seconds, but in the early 1980s, a new category of pulsar was discovered, the millisecond pulsar. So something must have sped these pulsars up, because our models for how the formation of pulsars from massive stars go wouldn't allow them to be spinning this fast. But material falling inward from a companion star, striking the star parallel to the surface and exploding, could speed up the rotation of a neutron star. So millisecond pulsars are thought to be spun up by matter falling in from a companion. This globular cluster has been found to have 108 separate X-ray sources, about half of which are thought to be millisecond pulsars. And everything in a globular cluster is pretty old. So now there's a few other weird versions of neutron stars. There are magnetars. A magnetar is a star that where the magnetic field is 1,000 times stronger than a pulsar. So some examples, SGR 1806-20, it's about 40,000 light years away. It burst in 2004 and released more energy in a fraction of a second than our sun did in over 100,000 years. It's believed to have a neutron core with a mile-thick iron surface that enhances the magnetic field. This structure and the stresses on the surface can produce cracks and star quakes, releasing tremendous amounts of energy. So these things are crazy. So what causes gamma ray bursts? So we talk about X-ray bursts, but we also see gamma ray bursts. And the way gamma ray bursts were first detected is kind of hilarious. They were first detected by military satellites, put up as part of the processes for the nuclear test ban treaty. Whose purpose was to detect if anybody was testing nuclear weapons, because nuclear weapons release gamma rays. But we were seeing bursts of gamma rays coming from not Earth, from space. So here is the source of a gamma ray burst. This is the host galaxy it's from. You can see it brightening up and dimming over a period of time. So these are some specific, there's this burst from this galaxy. So gamma ray bursts are these brief bursts of gamma rays coming from space. They were first detected in the 1960s. Truly by accident. They were detected by a military program, military satellites that were looking for gamma rays from nuclear detonations on Earth as part of, we wanted to know if anybody was testing nuclear weapons. But we were seeing gamma rays from space, not from Earth. So now thousands of these gamma ray bursts have been detected. It's very difficult to pinpoint their locations because gamma ray telescopes have poor resolution because it's extremely hard to focus gamma rays because they're so high energy that you can't bounce them off a mirror or bend them with a lens because they just violently interact with whatever they hit. So it's very hard to get good images with gamma rays. So it's difficult to identify optical or radio counterpart for gamma ray bursts. We've finally been able to detect optical sources in a few cases, and they were found to be billions of light years away. Gamma ray bursts are far away from us. Now, it's thought that gamma ray bursts are related to neutron stars as well. So gamma ray bursts occur and were first spotted. So they also occur. They were first spotted by satellites looking for violations of nuclear test ban treaties. So we put up satellites to make sure nobody was cheating on the nuclear test ban. The whole nuclear test ban treaty was all about constantly proving to everyone else that you weren't testing nuclear weapons and stuff. So not only did you mothball these planes, you mothballed them all out in a desert where anyone could take pictures from space, kind of thing. So there was a lot of that going on during the nuclear test ban treaty process. So this map of where bursts have been observed shows no clumping of bursts anywhere, particularly not within the Milky Way. So the bursts must originate from outside our galaxy. And when we finally identified an optical source, it was billions of light years away. So distant galaxies. Here are some sample curves plotting some gamma ray intensity versus time for gamma ray bursts. You have some short ones and some longer ones. So some gamma ray bursts are just a fraction of a second or maybe a second, while some could persist for minutes or even hours. They basically come in two types. We've observed two types: short gamma ray bursts and long gamma ray bursts. Now, the long duration bursts that last more than 2 seconds are thought to be caused by the collapse of a star, which has lost its outer layers of hydrogen. And energy gets beamed out, which can create these gamma ray bursts. This is a star. This is what's known as a hypernova, and it occurs when the core collapses to form a black hole, but the outer part of the star doesn't completely dissipate. And the whole thing sort of pauses for a little before it collapses again and violently extinguishes. While short duration bursts that last less than 2 seconds are thought to be caused by colliding neutron stars. And we've observed evidence of, we know colliding neutron stars happen because we've observed gravitational waves from those neutron star collisions and observed the we've actually succeeded in both observing the gravitational wave and observing the optical or electromagnetic source for neutron star mergers. So so the kilonova are these large. It's thought that the longer duration bursts are caused by kilonovas, which are these collapse of the star, which has lost its outer layers of hydrogen. And the short duration bursts are caused by colliding neutron stars. So observations in the 1990s showed that many gamma ray bursts were coming from very distant galaxies. So these need to be among the most powerful explosions in the universe, and could be the formation of black holes. And the distant measurements of some gamma ray bursts show them to be very far away, something like 2 billion parsecs for the first one measured. So occasionally the spectrum of a burst can be measured, allowing us to figure out its distance, but it's pretty rare. It's hard to measure the distance to these gamma ray bursts. So observations show that at least some gamma ray bursts are produced by supernova, very massive supernova explosions. Some others may come from collisions between neutron stars. So these are one of those massive supernova explosions, which can be observed optically for a few days. But for several days, this is like a couple of weeks, but others may come from collisions between neutron stars. So the long duration bursts are thought to be caused by these hypernovas. These could be also from colliding neutron stars. So 2 models, the merging of neutron stars or a hypernova, have been proposed as the source of gamma ray bursts. For neutron stars, if you have a binary system of 2 neutron stars, they're going to steadily lose energy and get closer and closer, and then they're going to coalesce and merge, creating a very high temperature accretion disk and basically explode. And as they collapse into a black hole, matter will explode outwards, creating a gamma ray burst. There'll be a relativistic outflow of material. But you can have also a hypernova, where you have a collapsing star, where the supernova stalls and a black hole forms, and the accretion disk restarts the supernova, and you get a supernova on top of this merger. So this burst, for example, looks like much like an exceptionally strong supernova, leading credence to the hypernova model. However, we've also observed neutron star mergers. So the general thought is that actually the 2 types are the 2 different types of gamma ray bursts. So let's talk a bit about general relativity, because we're going to talk about black holes. And to talk about black holes, we need to talk a bit about general relativity. So, general relativity was put forth by Albert Einstein in 1916. And it was a new description of how gravity works. So he was sort of, in 1905, he put forth special relativity, which resolved this issue of the fact that there was no apparent speed difference for light, depending on the direction it was in, even though the Earth was clearly moving through space. So there should have been. So this is a new description of how gravity works. Newton's gravity works in almost every situation. But it cannot explain motion near strong sources of gravity, which is why you need general relativity, and it cannot explain motion at high speeds, near the speed of light, which is what special relativity handles. So special relativity handles movement at high speeds, and it's special because it doesn't include acceleration. General relativity includes acceleration and gravity, and it explains that. So general relativity explains gravity as the bending of space and time instead of a force between objects. So special relativity is built off this idea that the speed of light is the fastest you can go, and no matter what you're doing, you will always observe light moving at the speed of light. So the speed of light is the maximum possible speed, and it's always measured to have the same value by all observers. Given that idea, you can take that and work from it to basically extract the ideas of special relativity. It's kind of brilliant, and it's not that hard to follow. Like the math of special relativity is not that hard. You can do it with just high school level algebra. You don't need anything deeply advanced. So there's no absolute frame of reference, there's no absolute state of rest. You can't tell the difference between moving at a constant velocity or being at rest. Space and time are not independent, but are rather unified as space-time. So that's what you build up, that's special relativity, and then you build off of that into a more general model of general relativity. So special relativity was built around this idea that if you're moving at constant velocity that in a sealed room, like if you're moving at constant velocity, there's no way you can differentiate that from standing still. Einstein then went on for general relativity to propose that in a sealed room, the experiment can determine the difference between a weightless object in space far away from any sources of gravity or a freely falling object. So here we're starting to have gravity, or an object being accelerated by a force compared to an object in a gravitational field with the same acceleration. So this is general relativity. This is adding an acceleration in gravity. There's no way to differentiate between free falling in a gravity field or just floating in space far away from all gravity, or differentiate between being in an accelerating box or standing in a gravity field. So it's impossible to tell within a closed system whether one's in a gravitational field or accelerating. If you're in an elevator in a gravitational field, you feel pulled down by gravity. If you're in an elevator that's accelerating upwards, you feel pulled down by inertia tied to the accelerating elevator. And there's no way to differentiate them, so at some level they must be equivalent. So what does this mean for light? So you can ask the question, does light travel in a straight line? And the answer is no. Light is affected by gravity, it bends in gravitational fields. And if you imagine a rocket sitting on Earth, the light beam should travel straight across the crack and strike the other side. But if you imagine the same rocket accelerating through space, the light would hit at a lower point because of the acceleration of the rocket. However, the equivalence principle states you can't distinguish these situations, so gravity has to bend light. And this is definitely true. We have observed gravity bending light. So how can light be bent by gravity? Well, if space and time themselves are bent by gravitational fields, if what's happening is not so much that there is a gravitational field, but that space and time are bent, then traveling in a straight line is just being bent by gravity. If you follow the shortest path through the deformed space-time, that will have that curved path. So this causes it not to follow a straight line path. And the amount of distortion of space-time depends on the mass of the object. More massive objects create more distortion. And so that's the big idea of general relativity. Unfortunately, unlike special relativity, the math of general relativity is not easy. And I would not suggest it out of curiosity, because it is in fact really ugly. But special relativity, the math is quite straightforward and approachable. So mass will distort space-time around it. Objects follow the shortest path in this distorted space-time, and a more massive object will distort space-time to a greater extent. So this is the distortion of the Earth. If you have a more massive object, you get more distortion. It's usually expressed by showing it like a bent sheet of rubber, kind of idea. So matter tends to warp spacetime, and in doing so redefines straight lines, the path a light beam would take. And a black hole occurs when the indentation caused by spacetime, caused by the mass of the hole, becomes effectively infinitely deep. So once you hit a point where
the mass disturbs space-time enough, you'll get what is mathematically called a singularity, which is an infinity. So an infinitely deep hole caused by space-time, that's a black hole. So some of the tests we've done for general relativity. Well, one of the ways that Newtonian gravitational models failed was in the orbit of Mercury. So the orbit of Mercury precesses around the sun. So over time, where the elliptical portion of it points changes, but the rate it precesses didn't match what was predicted by the Newtonian models. The perihelion position slowly changes. General relativity gives the correct value for this precession. Newton was off by 43 arc seconds per century. So there was a discrepancy, and general relativity gave the right answer. And additionally, we see gravitational lensing. We see the deflection of starlight by gravitational fields. We were able to observe stars close to the sun during an eclipse in 1919. And the shifts in their positions as the sun passed between us and them during the eclipse were what was predicted by general relativity. So we were basically able to see stars that if light traveled in straight lines, we wouldn't have been able to see. And we also saw stars change position slightly from the gravity of the sun, acting like a lens. So basically what happened is that light coming from the star got bent by the sun, and it deflected the path of the light from the star. So we saw stars basically that would have been behind the sun. Now, additionally, we see that time will slow down in the presence of a gravitational force. We can also observe this. We, in fact, have to correct for it. So GPS satellites work by time is affected both by how fast you're moving and by relative to each other and by gravity. So GPS satellites work by having very accurate clocks that send their time down to us, and we use that to figure out how far away they are from us. It turns out you have to correct for both the fact that they're orbiting the Earth, so they're moving fast, which effectively slows down their time, and that they're higher up above the Earth, so they're in a weaker gravitational field, which effectively speeds up their time. And you have to include both of those corrections in the satellites, otherwise your position on Earth would be off significantly. Like, I think you would drift like a mile a day or something. It's non-trivial. So a clock on the ground will run slower than a clock in orbit. That's something we had to correct for in GPS satellites. Additionally, there's something called gravitational redshift. Light escaping from a massive object can't slow down, because light always travels at the speed of light, but it has to lose energy. And so what happens is its wavelength gets stretched, because it must always travel at the speed of light, so the speed can't change. So what it looks like is that time is slowed down near a massive object. As the light basically gets stretched out. And we tend to think of relativity as only applying in extreme conditions, but it does actually affect us every day. GPS satellites are used to determine our position on Earth. These are traveling at high speeds, so the clocks slow down from special relativity. And they're also high above the Earth, where gravity is weaker, so the clocks speed up from general relativity. And the combined difference is about 38 microseconds per day. If this isn't taken into account and corrected for, the errors can amount to 7 miles per day in your GPS position. Because Your GPS position is based on the time difference from these satellites. So you need to know their time very accurately. So general relativity from Einstein in 1916 describes gravity as a bending of space and time. Many tests have been done, and each has been able to confirm the predictions of general relativity. And GPS satellites use both general and special relativity to locate you through your phone. So let's continue.
Just as there is a limit to the mass of a white dwarf, there is also a limit to the mass of a neutron star. For a collapsing stellar core with more than about 3 solar masses, neutron degeneracy pressure is not strong enough to overcome the crush of gravity, and the collapse continues without limit. The result is a black hole. In principle, all the mass of the collapsed core is compressed to infinite density at the central point called the singularity, but we can never detect anything from within the event horizon because that is where the escape velocity is the speed of light. To be sure you understand this idea, answer the following question. Why can't we detect events that occur inside the event horizon of a black hole? Is it because the strong gravity prevents events from occurring? Because the blackness snuffs out any light from these events? Or because light cannot escape the black hole's gravitational pull? The answer is C. Inside the event horizon, the escape velocity is greater than the speed of light, so light itself cannot escape the black hole's gravitational pull. Given that no light can escape from black holes, you might wonder how we could ever detect them. The answer is that much like white dwarfs, both neutron stars and black holes can be surrounded by an accretion disk in close binary systems. The strong gravity makes these disks hot enough to emit X-rays, so we can detect them as X-ray binaries. In many cases, we know the mass of the companion star, so we can calculate the mass of the unseen object from the system's orbital properties. If the mass is above the limit for a neutron star, as it is for the system called Cygnus X1 and many other systems, then we conclude that the system harbors a black hole. A second way of identifying black holes comes from binary systems that contain 2 black holes. Einstein's general theory of relativity tells us that these systems will lose energy by emitting gravitational waves, causing the orbits to decay until the 2 black holes ultimately merge. The merger will produce a particularly intense burst of gravitational waves. Such a signal was first detected in 2015 by the LIGO gravitational wave antennas, providing direct evidence for the existence of black holes.
One of the hilarious things about that particular observation was they just upgraded it. They got this observation like almost immediately after starting their run. They just got it started. They were, hopefully we'll see something. And then like next day, bang, actual gravitational wave station. It was a big deal. I remember when this happened, it was a real big deal. So what's a black hole? So a black hole is a point where gravity wins. If an object gets dense enough, its gravitational field gets strong enough to basically cut it off from the rest of the universe. You get an event horizon, and then the event horizon is basically a one-way path. You can go in the event horizon, but you can never come out. You are decoupled from the rest of the universe. So the curvature of space-time gets greater and greater as we approach a black hole, and the black hole is basically a bottomless pit in space-time. So it's a black hole is an object with gravity that is strong enough that nothing, including light, would be able to escape. And the idea of something with strong enough gravity that not even light would be able to escape was first considered in the 1700s. So Laplace and Mitchell considered the idea of some object that was dense enough that its escape velocity was greater than the speed of light. But no one knew that the speed of light was the speed limit for the universe at that point, because it was the 1700s. But you could conceive of saying, okay, light travels so fast, you could have an object that had gravity that was so strong that not even like that, to escape it, you'd have to go faster than light. And basically what you can do is if you imagine an object that gets compacted smaller and smaller, as the size decreases, the gravitational force at the surface increases, and eventually you hit a point where gravity is so strong, not even light would be able to escape. So a black hole is an object where gravity is so powerful that not even light can escape it. Some massive star supernovae can make a black hole if enough mass falls into the core. This is one of the ways that black holes are generated. This is how we get the smaller black holes. There are also these supermassive black holes in the centers of galaxies that are clearly generated by some other process. And the mass of a neutron star can exceed about 3 solar masses. So if the core remnant is more massive than that, nothing will stop its collapse, and it will become smaller and smaller and denser. And eventually the gravitational force is so intense that even light can't escape, and the remnant will become a black hole. So you can calculate the escape velocity of an object by calculating the change in kinetic energy, instead setting that equal to the change in gravitational potential energy. And you basically get escape velocity squared over 2 equals g times the mass over the radius. And light would not be able to escape Earth's surface. You could shrink it to less than 1 centimeter. And this size, this radius, where the escape velocity is greater than the speed of light. So if you plug in the speed of light for escape velocity here and solve for radius, you get the radius is 2g times the mass divided by c squared. That is called the Schwarzschild radius, and that is the size of the event horizon of a black hole if it's not spinning. It gets weirder when it's spinning. Because there's an effect from the spinning, but it's roughly the size of the event horizon of a black hole. If it's spinning, the black hole is in a perfect sphere anyway. So gravity is just a curvature of space-time. And as an object shrinks, the curvature gets bigger and bigger. At enough curvature, even light gets bent back to a black hole. So near a massive object, if it's less massive or less dense, light travels outwards. But near a very massive object, light gets bent back. And in fact, even just outside a black hole, we can observe light basically orbiting around it or being bent around the black hole. The rays are not being pulled by a force, but are following the only path they can in this highly distorted space-time. And the surface of a black hole is the radius at which the escape velocity equals the speed of light. And this spherical surface is known as the event horizon. And the radius of the event horizon is known as the Schwarzschild radius, because it was calculated first by Schwarzschild. And this is actually pretty easy to calculate. It's 2g times the mass over c squared. You just set the change in kinetic energy equal to the gravitational potential energy required. And past the event horizon, we have no knowledge of anything that occurs within the event horizon. We can't really know anything within the event horizon. It's cut off from the rest of the universe. And the Schwarzschild radius is the mathematical determination of the distance to the event horizon. The larger the mass, the bigger the Schwarzschild radius. It's linear in mass, actually. And in the center of this is the singularity. It's a theoretical point of infinite density at the center of a black hole. But we don't really know, because increasing things to infinite density breaks physics, or our understanding of physics. So we have no idea what's going on inside, and it's cut off from the rest of the universe anyways. Now, most black holes are actually spinning, and that makes them not quite perfect spheres. They bulge a little at the edge, basically, but it's very similar in size. So a 3 solar mass black hole is also about as big as a small city. Neutron star is a little bigger, the black hole is a little smaller. A black hole's mass strongly warps space and time in the vicinity of the evading horizon. Use a two-dimensional depiction of space-time. And as you add gravity, the circles get more widely separated near the mass, so the curvature is greater. And then this is what a black hole looks like. They get even more and more stretched, and you eventually get infinite stretching. It's a bottomless pit. So the radius for escape speed from a black hole equals the speed of light. It's called the Schwarzschild radius. Earth's Schwarzschild radius is about a centimeter. The sun's is about 3 kilometers. Once the black hole is collapsed, the Schwarzschild radius takes on another meaning. It's the event horizon. And nothing within the event horizon can escape the black hole. So nothing can escape from within the event horizon because nothing can go faster than light. And no escape means that there is no more contact with something that falls in. It increases the hole's mass, will change its spin or charge, but it otherwise loses its identity. Black holes are in fact defined by 3 numbers. Mass, angular momentum, or how fast they're spinning, and charge, what their charge is. All other identity or information is lost. So black holes have only 3 properties: mass, how much matter it contains, the electric charge, the net positive or negative charge, and the angular momentum, how fast the black hole spins. And theoretically, or at least to the best of our understanding, theoretically, the mass collapses down to a single point or a singularity, where space and time effectively no longer exist. And it's questionable if a singularity even exists, but like basically all our models of the universe break down under the extreme conditions of a black hole. What would be going to like if you talk about a little ways inside, we can model that, but when we get close to the singularity or what might be the singularity, like what's happening is it's called the singularity because there's a mathematical singularity. That's what comes out of the math. And mathematical singularities are usually bad things because they're infinities. So basically, as far as we know, beyond the neutron star limit, no known force could resist the crush of gravity. The general theory of relativity predicts that gravity crushes all matter into a single point known as a singularity. But this causes problems with quantum physics. So we really don't know what really happens. We just know that like our current models of physics break down in this extreme situation. And we can't even look at it to get an idea of what's going on. So, how big are black holes? Well, the size of a black hole depends only on the mass. If you compressed Earth to a black hole, its event horizon would be about a centimeter. It would be less than a centimeter. Compress the sun to a black hole, its event horizon would be about 3 kilometers. Compress the galaxy to a black hole, the event horizon is 0.1 light years. That is bigger than, well, that's not necessarily bigger than most planets. There's some big ass. So black holes vary in size from a few solar masses that were created in the deaths of stars up to supermassive black holes that can be billions of solar masses. Black holes are cosmic vacuum cleaners. The unusual effects of a black hole are really only noticed close to the event horizon, within a few times the Schwarzschild radius. So, for example, if the sun were suddenly replaced with a black hole of the same mass as the sun, the Earth's orbit would remain unchanged. Very strange things would happen close to the sun, but not much further away. So basically, like, they're not cosmic vacuum cleaners. They're not like sucking up everything around. The weird stuff happens close to the black hole. Some weird stuff happens close to the black hole, but it is close to the black hole. So again, black holes have only three properties: the mass, how much matter they contain, their electrical charge, the net positive and negative charge, and their angular momentum, how the black hole spins. And theoretically, all the matter collapses down to a point or something. So what might it be like to visit a black hole? So near a black hole, the curvature of space-time gets greater and greater as we approach, and the black hole is basically a bottomless pit. So if you travel towards a black hole, what would you notice? As you watch something approach a black hole, we'll see the clocks of that person start to run more slowly. We'll notice the gravitational redshift from their signals becoming infinite, reaching the event horizon. So they get redder and redder and fainter. And eventually, you would appear to stop at the event horizon. To the astronaut, everything would appear normal as you cross the event horizon. Assuming the black hole is big enough that there is not extreme tidal forces. If you're going towards a smaller black hole, you will undergo what is known as spaghettification, where you are torn apart by the tidal forces. But if you're going towards a supermassive black hole, the tidal forces aren't nearly as extreme. So here's sort of a voyage through a black hole. And this is, sort of summary of what black holes are. Black holes are when gravity wins.
In your textbook and the chapter overview video, we've discussed the strong evidence indicating that black holes really exist. But what exactly is a black hole, and what would it be like to visit one? We'll consider these questions in this video. The idea of a black hole was first suggested more than 200 years ago, based on the possibility that there might be objects with an escape velocity greater than the speed of light. Recall that escape velocity is the speed that an object must have in order to leave orbit of a planet or other object. For example, the escape velocity from Earth's surface is about 40,000 kilometers per hour, or 11 kilometers per second. However, if we could somehow shrink Earth in size, the strength of gravity on Earth's surface would grow stronger, making the escape velocity larger. In principle, there is a size at which Earth's mass would be so compressed that the escape velocity would exceed the speed of light of 300,000 kilometers per second, in which case not even light could escape from the surface. This captures the basic idea of a black hole as an object with gravity so strong that not even light can escape from it. The boundary within which light cannot escape is called the event horizon, which marks the place at which the escape velocity is the speed of light. However, rather than being the surface of a highly compressed object, the event horizon hides everything within it, and all the mass has in principle been crushed to the point we call the singularity. Moreover, we now understand black holes in terms of Einstein's general theory of relativity, which tells us that gravity causes distortion of the structure of space and time, or space-time. We cannot visualize all four dimensions of space-time simultaneously, so we instead use two-dimensional analogies. We begin with a flat rubber sheet, representing space-time far from any massive object. A massive object, like a star, causes space-time to curve, much like the rubber sheet would curve with a heavy ball placed upon it. The denser we make the ball, the more it will curve the rubber sheet, and in our analogy, a black hole is a bottomless pit in space-time, with the event horizon marking the boundary from which nothing, not even light, can escape. Keep in mind that the rubber sheet is only an analogy meant to illustrate the extreme distortion of space-time near the event horizon. In reality, a black hole is spherical, as we see in this computer simulation looking toward a black hole with stars behind it. The strange arcs of light and double images of stars are caused by the way the black hole distorts space and time. We usually describe the size of a black hole by what we call its Schwarzschild radius, which is the radius its event horizon would have if we neglected the distortion of space-time. It is given by this simple formula, 3 kilometers times the mass of the black hole in solar masses. For example, a 10 solar mass black hole would have a Schwarzschild radius of 30 kilometers. Before we continue, check your understanding of the formula, which we have moved to the bottom of the screen, by answering this question. What is the Schwarzschild radius of a 1 billion solar mass black hole? Would it be 1 billion kilometers, 3 billion kilometers, 300 billion kilometers, or 1/3 of a billion kilometers? The answer is B. We simply put in 1 billion for the mass in solar masses, and multiplying by 3 kilometers gives a Schwarzschild radius of 3 billion kilometers. We chose these examples to illustrate the fact that there are two general categories of black holes known to astronomers. The black holes that form when massive stars die in supernova explosions typically have Schwarzschild radii of tens of kilometers, or roughly the size of Rhode Island, the smallest state. But we also find supermassive black holes in the centers of galaxies, and some of these have masses a billion or more times that of the Sun, giving them Schwarzschild radii as large as the orbits of the outermost planets in our solar system. For our final topic in this video, let's turn to the question of what it would be like to visit a black hole. We'll assume you are visiting a black hole formed from the death of a star, and not in a binary system like Cygnus X1, in which radiation from the accretion disk might quickly kill you. This animation imagines that you are orbiting the black hole while another spaceship is falling toward it. Notice that as you watch the second spaceship, you'll see its time run slower and its light become more redshifted as it approaches the event horizon. In fact, you'd never actually see it reach the event horizon because its time would in principle come to a stop at that point, and its redshift would grow too large for it to be observed by any conceivable technology. However, a person in the spaceship falling toward the black hole would not notice anything strange about his own time, and in fact, he'd very quickly fall past the event horizon and into the black hole. Unfortunately, he would not survive the journey, because the enormous mass and small size of the black hole means that gravity would be significantly stronger at his feet than his head, creating a lethal tidal force. The only known way that a person could in principle survive the journey across an event horizon would be if the visit were to a supermassive black hole, where the larger size would mean a much weaker tidal force. Still, according to current understanding of physics, no communication is possible from inside a black hole to outside it, so a traveler who crossed the event horizon could never tell the rest of us what he saw inside.
So that was what I want to cover for today. Just a reminder, Thursday this week is the test. You need to be here to take the test. Just a reminder, test is on Thursday, the 30th. So on Thursday this week, we will have the test. If you're not able to make it, make sure to send me, let me know in advance so then I can have afterwards work out a time for you to make it up. So the worksheets, homework number 3 are also due on 30th, Thursday, when we have the test. Yeah, that's all for today. I'll see you all for the test on Thursday. Have a nice day. Don't see. Nice day.